Hello and welcome to Brunei Math Club. In this video, we study the reduced echelon form. We have learned that a system of simultaneous linear equations like this one can be represented in terms of an augmented coefficient matrix. By applying a series of elementary row operations to this matrix, we get this simplified matrix. This is an example of the reduced echelon form. From this matrix, it's easy to get the solution. Okay, let's start. But before proceeding further, let us look at this matrix more closely. So what we notice about this matrix is that it looks like steps. And there are three steps in this matrix. And below the steps, the elements are all zeros. And for each row, the leftmost non-zero element is always 1. And above those ones are zeros. And everything else can be anything. So these are the defining properties of the reduced echelon form. Now we turn to more formal definition. Before we introduce the reduced echelon form, we first define the echelon form. So consider an m by n matrix. That matrix is said to be in the echelon form if the following holds. First, there may or may not be some columns, 1, 0, 1, or 2 or more columns that are all zeros. Then in the first row, we find the first non-zero element. So this is the leftmost non-zero element in the first row. And in this column, all the other elements below this element are zeros. And in the first row, all other elements in the first row can be anything. It can be 0 or something else. Next, let's consider the submatrix obtained by removing the first row and all the columns left of this first column with non-zero element in the first row. So we consider this part and do the same thing. So there may be or may not be some columns with all zeros. And we find the first non-zero element here, and below that element in the same column, all other elements are zeros. And other elements in this row, in the second row, can be anything. So it can be 0 or non-zero. And we repeat this over and over by taking the next smaller submatrix. So let's see. So let's pick this one next and do the same thing again and again. So after all, we have a matrix of this form. So there are steps like this, and step proceeds one by one. So there are no steps with two steps at the same time, because if we find one non-zero element as the leftmost element, non-zero element in a row, then all the other elements below that element are zero. So the step proceeds one step at a time, right? So this is the echelon form of a matrix. So that was a hand-waving explanation of the echelon form, but now we want to define it more formally. So how can we do that? So here's the definition, more formal one, of the echelon form. So we have an n by n matrix. Let's say A, its elements are A, I, J. So this matrix is said to be in the echelon form if the following conditions are satisfied. So this matrix is said to be In the echelon form, if the following conditions are satisfied. So the condition is there exists an integer r. So this is the number of rows with non-zero elements actually. So this is an integer, and this r is greater than or equal to 0 and less than or equal to m. So this is the number of columns in the matrix. And for this integer r, there exist r integers, c1, c2, and so on up to cr. So these are integers and that are greater than or equal to 1, c1. c1 is greater than or equal to 1, and c2 is greater than c1, and so on. So this is an increasing numbers, sequence of numbers, and cr is less than or equal to n, the number of columns in the matrix. This r indicates the number of rows that contain non-zero elements, and these numbers c1, c2, cr means these columns c1, c2, and so on, and cr. So c1 is the column number that contains the leftmost non-zero element in the first row, and c2 similarly is the column number that contains the leftmost non-zero element in the second row, and so on. So we can find these numbers up to CR. So CR is the column number that contains the first non-zero element, the leftmost non-zero element in the rth row. For all other rows below that are all zero, so we don't need other numbers. So using these numbers R and C1, C2, and so on, we can define the echelon form in terms of the conditions these numbers should satisfy. So the first condition, if the row number I is between 1 and R, so if the row contains non-zero elements and the column number J is between 1 and Ci minus 1, then all the elements aij are 0. So that means, so I is the number of the row number that contains non-zero element, and ci is the column number that contains the leftmost non-zero element in that row. So this means, so let's take that row I, and ci is somewhere here, let's say. So this is ci. So this condition means the left of this column. So these these elements are all 0. And the second condition, if the row number is greater than r plus 1, then for all j, 1, 2, up to n, we have aij equals to 0. So these rows do not contain any non-zero element, so this makes sense, right? So all the elements in these rows are zeros. So that's what. And the last condition, AICI is non-zero for I equals to 1, 2, up to R. So this ICI element, so this is ICI element of the matrix, is non-zero. So this means for each row I, this indicates the leftmost non-zero element. So it should be non-zero, right? So that's it. So this is the formal definition of the echelon form. And this special element, AICI, is called a pivot or pivot point of the echelon form. And the column CI is called the pivot column or the pivot number. And the number R, the number of non-zero rows in the echelon form, is called the rank of the echelon form. So this notion of rank is important, and we'll come back to this later for more general matrices, not just the echelon form. Here is a simple quiz. Is this matrix in the echelon form? Yes or no? The answer is no. So what's wrong? Actually, this is wrong. So there are 4 rows, 1, 2, 3, 4, that contain non-zero elements. So in the language of the definition, R is 4. So for this R, there should be C1 greater than less than C2, which is less than C3, which is less than C4. So in this case, C1 is this one. So C1 is 1. And C2 is here. So C2 is the column 3. But what about C3? It's here. So C3 is also 3. So this is not strictly greater than 3. So this is wrong. By the way, C4 should be here. So it's 4. So this violates the definition of the echelon form. So this matrix cannot be in the echelon form. Now we are ready to define the reduced echelon form. Matrix A, which is an say n by n matrix, is to be in the reduced echelon form if the following conditions are satisfied. First, it's in the echelon form, of course. And second, all pivot elements are ones. So remember, a pivot point is pivot element is the leftmost non-zero element in the rows that contain non-zero elements. And third, that is easier to explain by picture. So we have an echelon form matrix. The pivot points are all ones due to this second condition. And the third condition is that all the elements above or below each pivot, they are zeros. Of course, there are no elements above the first pivot here, so it doesn't matter, but the below, they are all zero, of course. So if these three conditions are satisfied, the matrix A is said to be in the reduced echelon form. And although I don't show the formal proof, you can understand intuitively that any matrix can be transformed into a reduced echelon form by a series of elementary row operations. And also, the reduced echelon form of a matrix is unique. So there are no two distinct reduced echelon forms for a given matrix. It's unique. Only one reduced echelon form. I already explained in the beginning of this video that the matrix we obtained by solving a system of linear equation, we got this matrix 0, 1, 0, 9, 0, 0, 1, 2. So this was obtained from application of elementary row operation to an augmented matrix. So this matrix is in the reduced echelon form. As you can see, the pivot points are all ones, and the elements above or below the pivots are all zeros. And all other elements, which is not above or below the pivot, it can be anything. It can be zero or it can be non-zeros. So this is in the reduced echelon form. Finally, let us define the notion of the rank of a matrix, which we denote as this, rank A. We have already defined the rank of a matrix that is in the echelon form, which was the number of rows that contain non-zero elements. Since any matrix can be reduced into its reduced echelon form uniquely, the rank of this reduced echelon form can be used to define the rank of the matrix A, which is what we do. So the rank of matrix A is the rank of its reduced echelon form. Okay, that's all for this video. See you later. Bye. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.